Woohoo! Hello, hello. We are live. This is Math 40, section 4.1, Systems of Equations, page number 1, numero uno. And we're going to be talking in chapter 4 about what happens when we stick two lines together in the same plane, in the same graph together. And it actually could be like a hilarious sitcom, right? This line wants to go this way, this line wants to go that way. Let's see how these crazy kids solve all their problems. And the answer is that we're going to solve them with the help of Matt Damon. So first off, I want to talk about what a system is, because right off the bat I say systems of equations. And for our purposes, a system is a set of two, and then I'm going to write in or more, because you can have a system, you can have larger systems than this, but we're going to say a set of two lines or linear equations which are solved together. Which is more human than math. That's kind of regular speak, not math speak, but I think it kind of fits what we're trying to do. We're going to take two or more, but for us it's going to be two linear equations, so in other words lines, which are going to get solved at the same time. Now if you think about it, really think, I want to try to convince you that there are three different ways two lines can interact. The first way the two lines can interact is that they intersect in a single point. So there is one point in common. And that point is right there in the middle, this big old point. So that point exists on both lines. It's the intersection of the two lines or the two streets. Another possibility is if we have parallel lines, and remember parallel lines, the word parallel has parallel lines in it. That's how you remember it's got a double L. With parallel lines, the definition of parallel lines is effectively they have the same slope. They have no points in common. And the last one looks a little weird because you're going to look at this and go, wait a minute, there's only one line here. And there's the rub. There's actually two lines. They're on top of each other. Basically, the lines were the same line. Which, you know, it seems like it's more likely to happen in Shakespeare that you would have two lines that you don't recognize are actually the same line and hilarity ensues. But it turns out that this happens more often than you'd guess. Sometimes linear equations can get complicated. So you might have what looks like two different lines, but they are in fact the same line. And so here we have an infinite number of points in common. So I got a point there, point there. Any point that's on this one line is a point on both lines because they're the same line. So there are an infinite number of those guys. So what does it mean when I say solving them together? What does it mean to be a solution of a system? A solution is an ordered pair. Oh no. So much for, I'm afraid you're going to have to pay extra for spelling because that's just not going to happen today. XY, that says ordered. Just assume that gobbledygook says ordered in there. It's got enough letters. That would be correct spelling in the Middle Ages. I just want to say that, you know, so I'm historically accurate. A solution is an ordered pair if, which satisfies both equations. Okay, so you've got to be, this point is on this line, this point is also on this line, it satisfies both lines. Here, it's going to be impossible to find a point that satisfies both lines. Here, I've got all the points on the line are basically on both lines. So we're golden. We get a bunch of them. So now I hear you asking, what does Matt Damon have to do with anything? And the answer is Matt Damon is an actor and a director and a writer, and he is someone that our culture seems to love to see in peril. Every few years, we make yet another movie where he is lost at war, lost in a school, lost on Mars, and either we or he or a combination of people have to save him. And so I decided, just if that's what we want to do, let's go ahead and do that. So let's imagine Matt Damon is on another planet, say Mars. I don't know if that violates, trademark or copyright or anything like that, but let's just say Mars, and for no good reason. And we need to bring him home. And so the thing is there are two things we have to be able to do with our spaceship. One of the things we have to do with our spaceship to bring him home is to make sure we don't run out of oxygen. The other thing we have to do is we have to make sure there are heat shields, so that when it comes back through our atmosphere, the Earth's atmosphere is actually, when you come at it really fast, it's kind of like hitting a brick wall. There's a lot of friction. And so things heat up. That's, and go out and look up meteorites if you're curious about what this means. But basically, we want to design a spaceship so that he doesn't run out of oxygen, and he also does not, become a crispy critter on his way back into the atmosphere. So let's take a look at this first example. In this example, if this is the line of all the ways that we can design a spacecraft that will have enough oxygen, and this is the line that describes all the ways that it will not burn up on reentry. As we look here, this one point is the only place, this is the only design for a spacecraft that would have oxygen and not burn up. We could pick a point over here, and this would mean that there'd be lots of heat shields, but he'd have trouble breathing. We could pick a point here, he'd have a great time breathing, but it would get really warm when the spaceship tried to get back in through the atmosphere. So this is the point that we're looking for. So this is Matt Damon is happy. I'm going to skip over to this one. This, basically any spaceship that we make that would have enough oxygen for him would also be a spaceship that would have plenty of heat shields. What are the chances of that? Seems like a great coincidence. But so any spaceship we make that has one of the requirements will have the other one automatically. Now, this is a weird situation because some people are like, well, I could just do anything. And the answer is this point over here is not going to work. This point does not lie on that line. And so this one has neither. This is not going to have enough oxygen and not going to have enough heat shielding. So this is not a good point and not part of the solution. Write this in. Now, that brings us to the middle point, or the middle example. This is going to be the moment where we have the very dramatic, difficult conversation with Matt Damon over the magical radio that still works to Mars. I'm not sure how we set that up, but we did, let's assume. So here's the line for oxygen, here's the line for not burning up, and there is no shared point. So we're going to have to say, dude, we can build you a spacecraft, but you're going to have to decide, do you want oxygen or do you want it to be, a nice temperature inside? So this is a sad Matt Damon situation. Sad Matt Damon. Okay. So what I would like to do is practice to see, is this problem, this example that I've set up, is this problem a problem where Matt Damon is a happy guy, or is this a sad Matt Damon moment? So I've got two lines. Y equals x minus 2 and y equals 2 minus x. So they look very similar. They are not the same line, or at least they are not written in the same way. It does seem that they are different. So let's go ahead and plug in some values. Set up a table of values for each of these equations to find an ordered pair that satisfies both. So you know me, I always start with 0. So y equals 0 minus 2, which is negative 2. Plug in 1. 1 minus 2 equals negative 1. Plug in 2. 2 minus 0. 2 minus 2 equals 0. 3. 3 minus 2 equals 1. 4. You could keep going like this forever. You just create a table of values. These are all the points that are going to lie on this line. Now let's come over here and let's look at all the points over here. So I'm going to, again, start at 0. 2 minus 0 is 2. Now this one has 0, negative 2. This has 0, 2. That's not the same point. Drat. Okay, 1. 2 minus 1 is 1. So this one has 1, negative 1. This has 1, 1. Not the same point. Okay. 2. 2 minus 2 equals 0. Whoa, look at this. When x is 2, y is 0 for both lines. So the point 2, 0 is a solution for both equations. Therefore, 2, 0 is a solution to the system. There we go. Like I said, spelling's going to cost you extra, I'm afraid, today. Okay, we did it. That was page 1 of 4.1. I'll be back in just a little bit. We'll do page 2 and 4.1. Woohoo!